Welcome to the presentation of our MOVIKIT Robotics software modules. My name is Markus Müller. In the MAXOLUTION machine automation division at SEW-EURODRIVE, we design and develop innovative solutions which are precisely tailored to the needs of our customers. To do this, we develop standardized and thereby proven modules that can be flexibly and individually combined. In addition to the software modules, these also include the components of the drive and automation technology, as well as customer-specific mechatronic systems. Our robotic solutions are used in numerous industries and applications, such as the ones shown here in the food industry, in logistics in the form of distributed palletizing robots, or, for example, in large gantry robots with one or more drives per carriage that transport heavy loads such as stone, wood, and tires. In handling applications in the beverage industry, it is essential to make the robots move, for example, the drinks boxes on especially smooth motion profiles with a limited amount of jerk. In addition to conventional gantries with 2 to 5 axes, SCARA robots or single column palletizers with 3 or 4 axes are also frequently used. The advantage of the parallel kinematics shown here is their stiffness at relatively low dead weight. We support them from 2 to 6 axes. If fast speeds are crucial, the tripods with 3 to 5 axes stand out with a large work envelope. Our solutions are also perfectly suited for decorating food and processing workpieces. The wide variety of applications is a major challenge for the technology and software that is used. Even in seemingly identical applications from different manufacturers, there are almost always special distinguishing features that have been deliberately added and must be addressed on an individual basis. The products are also subject to continuous change, be it to increase their appeal for marketing purposes or because of changes in consumer behavior. Individual customer requests are increasingly leading to production on demand or even a batch size of just one item. Flexible adjustments are therefore the order of the day. It is accordingly all the more important to be able to easily and rapidly implement the continuous changes. In order to be prepared for the future, today's machine quasi even has to know what is coming tomorrow. Our answer to these challenges is consistent modularization. SEW-EURODRIVE has thereby been moving very successfully in the field of drive technology since it was founded 90 years ago. We have now also consistently transferred the modularization to the software and equipped it with automatic adaptation capabilities so that it can intelligently adapt to new products, for example. We also place a considerable amount of value on standardization for simple connectivity, not only externally via OPC UA and fieldbus profiles, but also by standardizing our own software modules in order to be able to flexibly combine customized solutions. From a modular system consisting of software modules which have been compatibly developed over many years. In the MOVI-C modular automation system, so-called MOVIKIT software modules for single-axis, technologies such as synchronous operation or camming, multiple axis applications like winders or storage retrieval systems, energy management, and much more can be combined, just like the MOVIKIT Robotics software module that I would like to present you today. The MOVIKIT Robotics software module, which, by the way, received the Handling Award for simple operation together with flexibility and performance capability, can be extended with additional robotic software modules that we call add-ons and are symbolized by the icons shown here. The medium models and large models add-ons provide kinematic models, the first thing that catches your eye when you examine a robotics application. They are divided into medium and large models due to the dual-use relevance of the 5- and 6-axis robots. It is our claim to be able to control all of the robots that our customers design or invent. Accordingly, a wide range of kinematic models already exists that we would be delighted to extend for your special kinematics. It covers numerous versions of the basic models that are Cartesian gantry robots with a typical arrangement of the main axis along the Cartesian coordinates x, y, and z, as well as roller gantries in which the tool is moved in a plane by a circulating belt using stationary drives in this plane. The advantage is the relatively low mass that is moved and the reduction in the number of cable carriers. SCARA robots have a similar design to the human arm with a shoulder, elbow, and wrist, and are used in upright as well as horizontal versions. Articulated arm robots have the greatest degree of freedom among the open kinematic chains. They are available with 6 rotary axes or as a combination of linear and rotary axes. Delta robots are parallel kinematics with 2 to 6 kinematic subchains. A duopod with 2 axes is shown on the left. The tripods have 3 rotary or linear main axes and optionally other rotary axes or tilt axes. In addition to the rotation symmetrical arrangement of the arms, we also support the 90-degree angle arrangement that makes very close placement of tripods in picker lines possible. Quadropods are available as cable robots for camera control in stadiums or as bar kinematics with 4 degrees of freedom, for example. And last but not least, hexapods provide the most degrees of freedom among parallel kinematics and can move large masses with high precision. The kinematic models not only allow modular selection, but also modular combination with different axis types. For example, real or virtual axis, as well as our multi-axis controller that provides synchronous and controlled motion of 2 drives or of other cascaded multi-axis controllers. Application examples include hoists and overhead gantries, for which a drive at each side provides motion in the same direction. The motion of another 2 drives or even groups of 2 drives each at either side can be controlled in further cascades. Further transformations are possible by means of modular combination. For example, the formation of couplings between the axes by transferring the torque using parallelograms or belts. Couplings such as this are also located between the hand axes of articulated arm robots. Imagine a SCARA robot with a rotary joint axis, for example. If you wish to drive the rotary joint axis by means of a linear motor, you can combine this crank with a rotary joint by means of a modular combination. There are linear lifting axes of gantries or single column palletizers, with which the effective coil diameter of the rotary drive changes during the lifting motion. To linearize the motion, you can either use an external encoder or use the motor encoder that is already present in combination with a modular transformation. With static coordinate systems, you can always use the same robot program with the same positions for pallets that are somewhat displaced or twisted, for example. If the pallets or parts to be picked are in motion on a conveyor belt, the MOVIKIT Robotics add-on conveyor tracking software module is used. Multiple robots on a conveyor belt can thereby sync up and pick or place parts or perform processing tasks on the workpieces that are passing by. The add-on is just as suitable for linear conveyor belt tracking as it is for rotary table tracking. A rotary table can also extend the robot's degrees of freedom using automatic, synchronous control by the robot, shown in the example with a robot moving in one dimension with a two-dimensional cutting task. Another example would be a three-axis robot that can accomplish a four-dimensional palletizing task by means of the additional degree of freedom of a rotary table, for example. All of this can be commissioned in a very simple and intuitive way, starting with configuration and parameterization in the MOVISUITE engineering software. In the example which is shown here, a robot software module from the catalog is attached to a MOVI-C controller using drag and drop, to which two MOVI-Drive axes are attached. In the robot software module, the right kinematic model is selected and the arm lengths, software limit switches, and emergency stop ramps are parameterized, for example. The right IEC project. It is the program code of the configured software module, is automatically generated by MOVISUITE so that the robot can be simulated, for example, and moved directly in an office environment. Here too, we made a conscious decision to make the entry of the robot movement simple using an interpreter. In this example, the robot is moved upside down and then moved back again accordingly after a snap-in point. The pose variables used here can be taught or edited in the variable list, for example, as can the motion parameters, Boolean variables, and real variables. The progress of the program is displayed using program and motion pointers. There is a large instruction set consisting of motion commands and subroutine calls, for example. A while loop is inserted here, and the end is set accordingly so that the robot now executes the movement until the loop condition is no longer fulfilled. As a straight continuation of the simple entry in the interpreter, we have also designed the user interface to be used on a mobile keypad to allow the motion sequences and coordinates to be easily adapted directly on the machine by means of parameterization without requiring the services of an IEC specialist. Simulated and real axis can be run on the machine in alternation, for example, supported by the integrated 3D simulation function in both cases. Furthermore, the user interface can also be combined with the SEW visualization to produce application-specific machine visualizations. If a pneumatic gripper is used, for example, it is important to switch on the vacuum for a certain amount of time, e.g. 200 milliseconds before reaching the product. When applying adhesive or in plotter applications, for example, switching events are also required in certain locations on the path. This can be implemented very easily using path events. For example, you can parameterize whether the path event should refer to the start or the end of the respective path segment. A master-based offset and a lead time or an after-run time are also parameterizable. The master-based and time-based parameterization can also be combined, resulting in the desired shift of the path event even over several path segments. That is very useful with a sequence of very short path segments or when moving at variable override, for example. Whereas the path events make events relative to the programmed path possible, the motion path itself can be influenced by external trigger signals using the MOVIKIT Robotics add-on Touchprobe software module. When palletizing, for example, automatic intelligent adaptation of the movements to the product and stack height is possible in this way. With a Touchprobe sensor-based positioning, the top edge of the beverage crates is determined using a light barrier in the example shown here. Starting from this point, the robot then precisely travels a defined parameterizable distance to the pick or place location. The exact product or stack height therefore does not need to be known. This allows several layers of crates of different heights to be stacked without the individual robots having to know the exact height. The robots therefore flexibly and intelligently adapt their movements to the respective products, meaning that product changes do not require any additional programming and can be carried out accordingly quickly. The sensor-based positioning is activated in the robot program by means of registration, and the desired remaining travel in the measuring direction of the sensor is parameterized. Either the high-position touchprobe positions of the inverters are used, which are then transformed into a Cartesian position, or the trigger is carried out with somewhat lower position requirements using a freely selectable bool variable of the robot program, whereupon the actual positions of the axis, which are transmitted cyclically to the SEW controller, are used to determine the starting point of the sensor-based positioning. With sensor-based measurement, the touch probe measurement, the exact path position at the point in time of triggering is also determined. However, sensor-based positioning is not initiated directly. Instead, the Cartesian touch probe position, shown here as the blue level, can be used as the target point for the next placement procedure. This function is very useful if the sensor is covered by the gripped crates as in the example shown. because this prevents sensor-based positioning during placement. The robot can also move at high speed during placement because it can travel precisely to the previously measured touch probe position. The touch probe measurement is also activated in the robot program by means of registration. Since the robot never moves 100% exactly on the path due to small lag errors of the axis, which are always present, the Cartesian position, which is determined, is projected onto the robot path orthogonally to the measuring direction. In this way, the touch probe position can be used directly as the target position for the next cycle, without the robot drifting away to the side over time. In this example, the area from which the touch probe is to be activated is parameterized via a path event. Here in the simulation, the trigger is activated by another path event, as a result of which sensor-based positioning of 80 mm in length must be carried out. For diagnostic purposes, symbols are used in the program to indicate when and where the events have been triggered, as also shown here in the 3D simulation. As can be seen here, the robot has automatically carried out the sensor-based positioning and thereby the adaptation to the product height. For this parameterizable and powerful touch probe solution, SEW-EURODRIVE was named the winner at the I4 Challenge of the Basel Area Business and Innovation Organization. With the aid of the integrated drive configuration, the required torque curves for precisely this motion sequence can now be determined, for example. We deliberately use exactly the robot controller with the motion algorithms that are also used in the actual controller of the robot, so that the selected drives are then also really suitable. Accordingly, the motion paths can also be optimized offline with the aim of reducing the mechanical loads and reducing the cycle time and the energy used. Of course, the masses and mass moments of inertia of the moving bodies must be parameterized here. As a rule, these are available in the required format from the CAD program. Triggers are also set in the robot program to clearly identify the part of the motion that is to be analyzed. This results in torque curves that are used to select suitable motors and drives in the SEW workbench. In addition to the standard drives with the PXG and ZN gear units, the modular motor gear unit system also offers precision servo gear units for highly dynamic and also heavy-duty applications, meaning that nothing stands in the way of your optimal custom drive solution. The dynamic models of the robots used in the drive configuration are also used at runtime to detect any collisions with the environment. When doing so, the MOVIKIT Robotics add-on collision detection software module compares the measured motor currents with the expected motor currents and initiates the required reaction in the event of a collision. Let us first examine an application case in which a collision is undesired but potentially taken into account. In this example, a yogurt cup that is too tall has been erroneously fed in, causing the robot to immerse into the cup and leading to contamination. With active collision detection, the robot immediately detects the contact and can successfully avoid the damage. When this takes place, the collision is determined in a highly sensitive manner by means of deviations in the dimensions calculated using the dynamic model. In this application case, therefore, the system does not stop and contamination is avoided. These examples with a balloon and a yogurt container, each shown respectively with and without collision detection in slow motion, show how sensitively and rapidly the collision detection works. In the following application case, a collision occurs during a transfer movement where no incorrect placement onto a product that is too tall or askew is to be expected during the picking procedure. Without collision detection, this can lead to damage to the robot and leg errors of the axis and therefore a system standstill. With collision detection activated, however, in the event of a collision, the robot will be stopped immediately with path fidelity. Due to the unexpected collision, user intervention is still required, but with a decisive difference that the risk of damage or contamination is reduced by orders of magnitude. In contrast to the undesired collisions which have been examined so far, we also support the application case of a desired collision. In this case, contact is intentionally made in order to determine the flexible effective stack height. The major advantage of this function is that no expensive force torque sensor is required on the picker arm. Instead, the contact is detected by measuring the motor currents and evaluation using the dynamic model. So far, we have seen numerous options for modular combinations and approaches for the flexible design of applications. In order to be able to address special requirements on an even more individual basis, we use the approach of full integration in the IC. This is the robot programs can be completely parameterized and operated from the IEC. Conversely, the IEC code can also be executed in a synchronized manner from the robot programs, for example, for a clearly defined process data image. Standard fieldbus interfaces with automatically generated compatible robot programs are available for the optional simple connection to a higher level system controller on the one hand, and the flexible expandability of the interface is available for custom adaptations on the other hand. In both cases, the user utilizes the MOVISUITE engineering software to parameterize the process data of the fieldbus interface, such as the number of path points, the coordinates to be transmitted, and the resolution thereof, for example. Simple operation and integration into the system is also supported by standards, as shown in the PackML example here, thereby allowing machine operators to quickly familiarize regardless of the provider. We provide the PackML standard in the MOVIKIT automation framework, which incorporates numerous powerful software modules. The framework supports the interfaces defined by PackML, such as pack tags, as well as defined states and modes. A very attractive software module enables load sharing in picker lines. The open solution makes custom adaptations very easy. Simulation in an office environment makes suitable parameterization possible so that the product flow can be optimally distributed to the various robots. Another frequently requested software module is used for simple parameterizable layer formation in which the products are moved and bundled as required. This concludes the presentation of the modular MOVIKIT Robotics software modules for flexible and customized robotic solutions. Thank you for your attention, and I would be pleased to answer any questions you may have at any time.